Hi, I'm Ruby Lee from Hewlett-Packard. I'd like to talk to you today about processing multimedia information with general-purpose computers. What is multimedia? There has been a lot of hype, and we'd like to propose the following simple definition. Multimedia is the integration of visual, audio, textual, and sensory information. Hence, it is nothing more than the integration of different types of information, but all represented digitally. There are many types of visual information. For example, images are pictures taken from the real world, whereas graphics are pictures that are generated synthetically by a computer. Video is nothing more than a sequence of images played back at a certain rate, such as 30 frames per second, while animation is a sequence of graphics pictures. Both are just more complex forms of visual data. Audio information, likewise, has a spectrum of representations from 8 kHz voice quality audio up to 44.1 kHz stereo CD quality music. Even textual information comes in many different forms. Simple text is commonly entered through a keyboard into the computer, while handwritten text is a more complex form of textual information. Sensory information is also a type of multimedia information. For example, sensing whether the lights are on in the room and then controlling whether they should be turned on or off. All these are examples of multimedia information. It is the digitization of all forms of media that makes multimedia processing on a digital computer not only possible, but desirable. Media such as video and audio, usually represented in analog form, is now represented digitally as just a bunch of binary bits, just as all other forms of information now processed by computers. Here's what I'll cover in my talk. I'll describe some of the applications multimedia enables, why video compression and decompression is important, and also some of the current video compression standards. I'll discuss the approaches to multimedia support and talk about characteristics of multimedia benchmarks. Then I'll give a concrete example of a small set of multimedia instructions implemented in PA-RISC processors and the performance that they achieve. Finally, I'll close with a look at future directions. So what sort of new applications can multimedia enable? Well, I can think of at least two classes of such new applications. In the first class, we see a person accessing information that may have been prepared earlier and stored online somewhere. An example might be video lectures like this one, taped offline and then stored digitally online. Through a desktop or notebook computer, or some other device embedding a digital processor, users can access the video lectures any place at any time. I call this education on demand. It has similar characteristics as the more well-known entertainment application, video on demand or movies on demand. In such applications, the ability to access digital video may be more critical than the ability to produce it. In the second class of applications, communications is real-time between two people or two groups of people, rather than between a machine and a person. An example application is the distributed meeting room. This allows a team of geographically dispersed people working together on a common project to see, hear, and interact with each other as if they were in the same meeting room. Now, these are both communications type applications rather than computation type applications. While computers in the past have been used mainly as computation tools, they can also serve as communications tools today and in the future. You see, computers can facilitate seamless and more effective communications. When computers are used for such digital communications applications, they process what we have called multimedia information. While multimedia does not equate with video, Yet a lot of emphasis on multimedia information processing tends to be on video processing. Why is this? It's not because video is the most useful of the multimedia data types, but because it is probably the most challenging for computers today because of its enormous appetite for the computer's storage, bus, network resources. Besides, computers are already very adept at processing keyboard text, graphics, and even digital audio. For video to be feasible in today's desktops, it needs to be compressed. You see, we're sort of trading off compute power for reduced storage and network bandwidths in dealing with video information. When video is compressed, then merely to read video data or access video data, real-time video decompression is needed. If video data is compressed, then to be useful, there has to be common compression and decompression standards. Otherwise, people cannot share the digital video data, which would definitely limit its usefulness. So this brings us to the issue of which compression standard to select. Well, MPEG-1 is an international digital video compression standard with growing acceptance. It gives video quality comparable to analog VCRs at a bandwidth of around 1.5 megabits per second. It's no coincidence that this corresponds to the basic CD-ROM transfer rates. MPEG-1 also uses many compression techniques common to other video standards. This figure suggests that there's a hierarchical nesting of compression standards with increasing complexity as we progress outwards. For example, all of these standards use what's known as the discrete cosine transform. MPEG includes many of the still image compression techniques of JPEG, which is an international standard for photographic quality digital images. MPEG-1 is also a subset of MPEG-2, which is the international standard being rapidly adopted by the broadcast industry for production quality video. Motion JPEG is a non-standard video format that consists of a sequence of JPEG images. At the same time, H.261, an international standard developed by telecommunications people for digital video conferencing, is also like a simpler form of MPEG-1. Now this chart shows the bandwidth required for a compressed video bit stream versus the subjective visual fidelity. Clearly, the ideal video compression standard will be one that provides exceptional visual quality at the lowest bandwidth, something at the bottom right corner of this graph. This is not provided by the existing standards, where better visual quality tends to come with higher bandwidth costs. At the high end, production and broadcast visual quality is provided by Motion JPEG and MPEG-2, where MPEG-2 provides higher quality at the same bandwidth. In the next band of video standards, useful for applications such as computer-based training or the education on demand application we mentioned earlier, we see that MPEG-1 provides better visual quality than other standards at a bandwidth of around 1 to 1.5 megabits per second. At the lower bandwidths, such as 300 kilobits per second or less, we see that H.261 provides adequate visual quality for applications such as video conferencing and video mail. So while MPEG-1 is by no means the ideal video compression standard, yet it appears to be a reasonable choice. Some proprietary digital video compression standards implemented by software on PCs and Macs tend to have much lower visual fidelity. Because MPEG-1 is an international standard, and because it provides at least VCR visual quality, which consumers are accustomed to, it can potentially enable a larger variety of video applications. Also, any features implemented to accelerate MPEG-1 video will also be useful for accelerating many other international video and image standards. Hence, we will frequently refer to MPEG-1 decompression as an example in the rest of this talk. At this point, let's take a quick look of what actually is involved in MPEG video decompression. This is the flow chart of the key steps in MPEG decompression, comprising of 6 functional steps: header decode, Huffman and run length decode, inverse quantization, the inverse discrete cosine transform, motion compensation, and displaying. Now, without going into the detail of the compression techniques used, each step in this MPEG decompression flowchart represents the reversal of a particular compression technique that was used to remove either spatial, temporal, or encoding redundancies in compressing the original video into an MPEG 1-bit stream. How has multimedia processing been supported in computers? Let's take MPEG decompression as an example again. Initially, it was common to see it supported with 3 special-purpose chips, represented by the 3 colors in this figure. Each chip performed one or more of the decompression steps and could be used in combination with other chips to implement different compression algorithms. Later, the functions in these 3 special-purpose chips were combined into a single MPEG decompression chip. Still later, a single video decompression chip might support multiple standards, such as MPEG, JPEG, and H.261, through low-level firmware included with the chip. This approach is the hardwired algorithm approach, using special-purpose chips. An alternative approach to the use of a special-purpose chip is the use of a digital signal processor or a video processor. A digital signal processor, or DSP, can be programmed to perform many signal processing functions, like audio and modem processing. Real-time MPEG video processing would require a very high-end DSP, or more likely, a sophisticated video processor. This chart shows that in a general-purpose computer which already has a microprocessor and memory, MPEG decompression with this approach would require an extra DSP chip or video processor chip with its own private memory, which is needed for storing reference video frames and tables during the decode process. Another approach has been to implement MPEG decoding with special functional units inside the microprocessor itself. So for example, you could put a special MPEG decompression circuit block inside the microprocessor, or you could put more generalized graphics functional units inside the microprocessor to perform some of the operations otherwise done by a DSP or video processor chip. This has sometimes been called native signal processing, or NSP, when the microprocessor itself performs the function of the DSP. The approach that we will focus on in this talk is a type of native signal processing that is even more integrated into the core of a microprocessor. We call this intrinsic signal processing, or ISP. Intrinsic signal processing supports multimedia information processing in the very core functional units of the microprocessor. The fact that ISP also stands for Instruction Set Processor is an intended pun, since it is at the instruction level of the general-purpose processor that intrinsic signal processing occurs. Now, each of these approaches to MPEG decoding clearly has its advantages and disadvantages for different applications and different markets. When the end goal of the product is just to do MPEG video decoding, then a special-purpose MPEG chip might in fact be the lowest cost volume solution. On the other hand, if the goal of the product is broader and likely to change with time, then a programmable solution may be preferable. The approaches of DSP, NSP, and ISP all supply software programmability at some level. The advantage of a separate DSP or video processor chip is that it doesn't use up the resources of the microprocessor. However, it is an additional chip and additional memory that has to be provided at additional cost. With DSPs, programmability in a high-level language depends on DSP compilers, which are nowhere near as advanced as compilers for microprocessors. Now, the advantage of using the microprocessor itself is that high-level programming languages like C may readily be used for creating multimedia programs. The cost is also lowest since every general-purpose computer already contains a microprocessor. And in the case of intrinsic signal processing, no additional functional units even need to be added to the microprocessor itself. Let's consider for a moment what are the advantages for implementing something like video decompression in high-level software running on the microprocessor itself. The first advantage is that it facilitates the pervasiveness of video data because such software can be compiled and executed on any of the basic computer platforms. A software video decoder is also the lowest cost solution for general purpose computers since no additional hardware boards need to be purchased. A third advantage is that video decoder implemented in software provides the greatest flexibility in accommodating emerging standards and any improvements in algorithms. Another consideration is that it provides the smallest footprint and power requirement when computers are miniaturized to handheld or wearable forms, such as Dick Tracy type wristwatches or Star Trek type wearable communication devices. But perhaps one of the greatest advantages of doing video decompression with software running on a microprocessor is that decoding multiple streams of video can now be done almost transparently by just task switching between the decoding of different streams. This is commonly done for multiple software programs running on a computer. Now, as microprocessors continue to improve in performance, supporting multiple video streams would improve as well, with no special effort. On the other hand, supporting multiple video streams using a special purpose chip or DSP is harder because basically one such chip decodes one video stream at a time. In order to decode 2 video streams, you would generally need 2 such chips, or at least twice the amount of private video decode memory to support the simultaneous decoding of the 2 video streams. Hence, increasing the number of video streams decoded is not as trivial. Okay, so suppose we do use the microprocessor itself to process multimedia information. But is the microprocessor appropriately designed to handle multimedia data, such as digital video and audio data? Surely we should extend the benchmarks we use to improve the design of microprocessors with multimedia benchmarks. Eventually, a multimedia benchmark suite should include all levels of multimedia programs, from basic multimedia data access programs up through programs which ensure security and privacy of multimedia information, and programs which provide recognition of multimedia objects, such as handwriting, voice, or image recognition. Higher-level multimedia applications are then built on top of some of these lower-level multimedia programs. However, the fundamental ability to access all kinds of multimedia data, including time-dependent data like video and audio, lies at the core of the differences between current data processing and multimedia data processing. Hence, it is really important that programs performing basic functions such as video and audio decompression form the initial core benchmarks in such a multimedia benchmark suite. Let's look at a specific multimedia benchmark program. Let's use MPEG decompression again. Now, this pie chart shows the execution time distribution of the steps in the flowchart of the MPEG decompression program after fairly extensive algorithm and software optimizations have been performed. Fortunately, the inherently serial parts of this program, such as header decode and Huffman decode, take up a very small fraction of the execution time. The 3 largest steps of inverse discrete cosine transform, motion compensation, and display contain a great deal of data parallelism. That is, the same operations are performed on different pieces of data. For example, the inverse discrete cosine transform has to be performed on every 8x8 block of pixels for each of 3 color components for each frame every 33 milliseconds. Here there's a lot of parallelism that can be exploited at many different levels. If we take a closer look at the operations actually performed in the inverse discrete cosine transform, we see that there aren't any unusual operations. The most common operations are simple adds and subtracts, followed by shift and add operations, which are used to perform multiplications by constants. We see that load and store instructions comprise only 15% of the instructions needed for an IDCT. And conditional branches represent only a small fraction of the instructions executed. These 4 types of operations represent 70 to 80% of all the instructions executed in the IDCT step. Fortunately, they are also the operations common in many integer programs. Now let's try to generalize the differences and similarities between video programs and ordinary programs. The greatest difference in video data is that it is time dependent. Each frame of video is only interesting for a 33 millisecond time slot relative to the start of the video clip. And dropping a frame of video data is not disastrous. At a rate as low as 10 to 15 frames per second, motion appears smooth and video can be acceptable to humans. Another differentiator between video and ordinary programs seems to be the almost embarrassing amount of data parallelism present in video processing programs. A third characteristic is that video processing can usually be done with just 16-bit precision. See, pixels in each frame of video contain 3 color space components, each of which is a byte. For medical images, these may be 12 bits instead. However, intermediate processing of such data normally requires greater precision, with 16-bit precision being sufficient in most cases. A fourth characteristic is that the common operations performed on video data are no different than those performed on integer data by a microprocessor. The most common operations appear to be just plain old add and subtract. Other common operations are multiplication by constants and simple divisions, such as divide by 2 or the arithmetic mean. At this point, we like to discuss a concrete example, what we did with a PA-RISC microprocessor to accelerate multimedia processing. But first, I want to emphasize that our overall goal was to find the most cost-effective solution for multimedia processing, whether or not it involved changes to the microprocessor. Our methodology involved synergistic software and hardware enhancements. First, we optimized the algorithms and software in the MPEG Decompression program. We also used system-level optimizations wherever this was the most cost-effective solution. For example, in order to display the decompressed video on the computer screen, color conversion from YUV color space to the RGB color space has to be done. Now, this is a pretty straightforward task where further algorithm enhancements are unlikely, so software implementation is not particularly useful. It seems that this is more a frame buffer related task and hence more efficiently done by the graphics controller, which after all controls the frame buffer. However, the combination of these algorithms, software, and system optimizations was still not sufficient to achieve real-time MPEG decompression in our entry-level workstations. It was the addition of a very small set of multimedia enhancements to the PA-RISC microprocessor that finally enabled real-time MPEG-1 video decompression in software. The fact that such a minimal set was sufficient is also interesting. Here is a diagram showing the standard ALU and registers present in almost all microprocessors. ALU stands for the Arithmetic Logic Unit, which performs functions of addition, subtraction, and logical operations. An add instruction consists of reading two registers from the general register file, performing some operation in the standard ALU, and writing the result of this operation back into a general register. In a pipeline processor, like most RISC microprocessors, this would take one cycle to perform one such instruction, giving a compute rate of one operation per cycle. We now introduce a technique called Subword parallelism. Subword parallelism is defined as the parallel processing of narrower data using data paths optimized for words. So for example, if we divide each 32-bit word of the microprocessor in two 16-bit subwords, then each register conceptually holds two subwords in a single 32-bit word. In addition, we would now partition the standard ALU into two 16-bit halves so that the same operation will be performed simultaneously on the two 16-bit subwords in the same instruction during a single cycle of the machine. The hardware prevents computations on one subword from contaminating adjacent subwords. This is a form of SIMD parallelism, or SIMD parallelism, which stands for Single Instruction Multiple Data Parallelism, previously implemented only by very expensive, high-end supercomputers. Examples are the ILIAC 4 in the past and the connection machine more recently. But what we've done now is introduce SIMD parallelism into a small, simple RISC microprocessor without violating RISC design principles. Now, partitioning an ALU is really quite simple. As anyone familiar with two's complement adders will know, partitioning such an adder is equivalent to blocking the carry from one half of the ALU into the other half of the ALU. Blocking a carry is equivalent to just adding a single AND gate that prevents the carry from bit 16 of the ALU from propagating to bit 15 of the ALU. Now, since adders are often implemented with carry look-ahead techniques, there's essentially no delay to the time taken through the adder by this blocking of the carry. Since the same two's complement adder is used also for subtraction, parallel subword subtraction can also be easily implemented. This amounts only to replacing the AND gate with a 2-to-1 multiplexer. If we wanted to get two operations per cycle without the technique of subword parallelism, we would need to implement two standard ALUs and increase the number of ports in the register file by 2 additional read ports and 1 additional write port. But you might say, most microprocessors already have superscalar implementations with 2 ALUs. For example, all current PA-RISC processors are superscalar with at least 2 integer ALUs. Well, we merely partition each of these ALUs in the same manner using subword parallelism. This results in 4 operations every cycle, since each ALU is now capable of performing 2 16-bit operations per cycle through the technique of subword parallelism. Since superscalar processors allow the 2 ALUs to perform different instructions during the same cycle, we've actually implemented an even more sophisticated form of parallelism, which is often known as SIMD-MIMD, where MIMD stands for multiple instruction, multiple data, meaning that different instructions are carried out on different pieces of data at the same time. Subword parallelism provides for the SIMD part of the parallelism, while superscalar execution provides for the MIMD part of parallelism. This type of SIMD-MIMD parallelism is implemented in the superscalar PA-RISC processor known as the PA-7100LC. Now, future PA-RISC 2.0 machines, such as the PA-8000 processor, are based on 64-bit ALUs. Using the same technique of subword parallelism, we now get 8 operations per cycle in the PA-8000. This means that the peak processing bandwidth of the machine has increased 8 times for 16-bit operations. So for example, if the processor was running at 100 MHz with a normal peak execution rate of 100 million instructions per second, it can now execute 800 million operations per second with the technique of subword parallelism. Now, if the processor ran at 300 MHz, it would be able to execute 300 times 8, or the equivalent of 2.4 giga operations per second, using this technique. Hence, the subword parallel technique can dramatically increase the peak computation power of a processor at a very minimal cost. So what operations are actually available in the initial set of PA-RISC multimedia instructions? By the way, we call this MAX for Multimedia Acceleration Extensions. First of all, parallel subword addition and subtraction are supported. The difference is that both the usual modular arithmetic and saturation arithmetic is supported. We'll be discussing saturation arithmetic later on. MAX also includes parallel shift and add instructions, which allow multiplication by constants to be performed. It also includes the parallel average instruction, which performs an arithmetic mean on the parallel pairs of subwords in the 2 source registers. Actually, it's pretty amazing that these were the only processor additions needed to enable low-end workstations based on the PA-7100LC processor to achieve high-fidelity, real-time MPEG decompression in software. These simple general-purpose extensions to a microprocessor provided significant speed-up at essentially no cycle time impact, no schedule impact, and no area impact on the processor chip. The chip size did not increase at all, but rather some 0.2% of the chip area was filled in with additional gates needed to provide the subword parallelism. For the PA-7100LC chip, one could say that subword parallelism provided a more efficient utilization of the silicon area rather than increasing the chip size. Let's now look at these instructions in greater detail. For example, multiplication by constants. Word shift left and add instructions have always existed in PA-RISC processors, since the same functionality is used for load instructions which are indexed by unit size, 1 byte, 2 bytes, or 4 bytes. Shift left and add instructions are very useful for implementing multiplication by integer constants. But many of the constants found in the video algorithms are fractional constants. Some of them have small integer components as well. It turns out that shift right and add instructions are more efficient and accurate in implementing multiplication by fractional constants. Suppose we wish to multiply a sequence of input data x1, x2 through xn by the binary fraction 1.101. This is equivalent to taking the value x, adding x divided by 2, and then adding x divided by 8. This multiplication can be done with just 2 shift right and add instructions. The first instruction would do a parallel shift right by 1 bit and add, which performs the x plus x over 2 part of the operation, since the shift right by 1 bit performs the x over 2 function. Now, the second instruction does a parallel shift right by 3 bits and add function, which adds the term x over 8 to the result of the previous instruction to give the desired result of x plus x over 2 plus x over 8. If this is performed on 4 subwords each cycle, we have an effective rate of 2 multiplications per cycle. This can actually be faster than using a full-blown 16-bit hardware multiplier. Now, of course, shift and add instructions can only be used for constant multiplications. But if these are common, as is true for many optimized video algorithms, then the parallel shift and add instruction is perhaps one of the most effective ways to accomplish multiplication. The hardware required is just a pre-shifter in front of one port of the ALU, which shifts the operand right by 1, 2, or 3 bits before going into the adder. This pre-shifter tends to balance the ones complement circuit on the other port of the ALU, which is needed for doing subtraction. Let's now look at the parallel average instruction. This gives the arithmetic mean of pairs of subwords, which is a very common operation in many video and graphics algorithms. The average instruction involves just an add followed by a right shift of 1 bit. The beauty of the average instruction is that no overflows are possible. This is because during the right shift, the carry is shifted in when the least significant bit is shifted out. The least significant bit is truncated, which is usually acceptable, except in some cases of cascaded averages. For example, if the cascaded average represents a light intensity value, then successive truncation may cause the result to be lower than the true average. So what we have done is to provide a simple rounding function rather than a truncation function. What this does is that some of the time the rounded result is greater than the true average, and some of the time the rounded result is less than the true average. But if the results are spread evenly over the range of possibilities, then the net difference between our rounded average and the true average is 0. The particular round to odd function we chose is also simple to implement, being a single logical OR gate on the 2 least significant bits of the sum. This does not increase the time taken through the adder, since it can be done before the most significant bit of the sum is calculated. Unlike the average instruction, the other subword parallel instructions can generate overflows. Handling multiple overflows that can occur with each subword instruction is a pretty hairy business. Any performance benefit that one might get from doing such parallel arithmetic could easily be lost if one had to take long delays in handling overflows. If overflows were not detected when they should have been, then erroneous results could occur without any warning. Saturation arithmetic deals with these overflows correctly and efficiently. Take, for example, pixel values which represent light or color intensities. With 8-bit pixels, if 0 represents black and 255 represents white, then the value of 256 should not wrap around to 0, as is the default case with modular arithmetic. This would turn a white pixel into a black one and vice versa. A result of 256 should ideally be clipped to 255 so that it will remain in the correct part of the color spectrum. This illustrates what saturation arithmetic does. In saturation arithmetic, if a result exceeds the maximum representable value, it is clipped to this largest representable value. On the other hand, if the result is smaller than the smallest number representable in the range of the result, then it is clipped to that smallest value. In the PA-RISC multimedia extensions, we have defined 2 types of saturation arithmetic. Signed saturation is defined as having both operands and the result be signed integers. Unsigned saturation would normally be defined as taking 2 unsigned operands and producing an unsigned result. However, we found that with 16-bit operations, this is rarely useful. So what we have defined is a sort of mixed unsigned saturation, where one operand is unsigned, the other is signed, and the result is unsigned. A single subword parallel instruction with saturation arithmetic replaces the equivalent of 10 PA-RISC instructions in a 32-bit processor and 20 instructions in a 64-bit processor because of the overflow handling and result clamping that is performed. Now, while the prime reason for putting in saturation arithmetic is to handle parallel overflows, actually, it turns out that saturation arithmetic has many other useful properties. It allows functions which normally require conditional operations to be performed without such conditional operations. For example, it can be used to implement useful functions like finding the maximum and minimum of pairs of numbers in parallel. Let a register Rx contain the 4 subwords x1, x2, x3, and x4, and another register Ry contain the 4 subwords y1, y2, y3, and y4. We can find the maximum of each pair of subwords in just 2 instructions. First, we will subtract Ry from Rx. Now what this does is that for each subword, the resulting value would be x minus y if x were greater than y. But it would be 0 if x were less than or equal to y. This is because of unsigned saturation, since the resulting value in unsigned saturation must be no smaller than 0. The second add operation will add back the value Ry to the result of the first operation. Now, if the result of the first operation is x minus y, then now the result of the second operation would be x, which is the new maximum value, since x is greater than y. On the other hand, if x were less than or equal to y, the first instruction will result in 0, and the second instruction will bring it back to y, which is then the maximum of the 2 values. Note that these maximum functions are being done independently on the subwords in parallel with only 2 instructions by using saturation arithmetic. By a similar method, saturation arithmetic can be used to find absolute values or to clip results to arbitrary ranges, since this is like finding a new maximum or a new minimum value. Our definition of mixed unsigned saturation is particularly useful for the common case where signed 16-bit intermediate values have to be clipped to unsigned 8-bit results. While saturation arithmetic has been used in DSPs, our definition of unsigned saturation is perhaps a little unusual, and the use of it in general-purpose processors is also somewhat novel. Also, while shift left and add instructions have existed in the original PA-RISC architecture, shift right and add is new. Also, the average instruction is not normally found in the instruction set of general-purpose processors. We have described the individual multimedia instructions. What performance can be achieved overall in real multimedia programs with these simple extensions? Let's look at software MPEG video decompression. The first 2 columns of this chart show performance in frames per second obtained by PA-RISC platforms without multimedia instructions. The previous low-end platform running at 50 MHz attained 9.9 frames per second, whereas the previous high-end platform running at 99 MHz attained 18.7 frames per second. Now, these are respectable frame rates, but not real-time performance. The next 2 columns represent the performance achieved when using PA-RISC processors with multimedia enhancements, namely the 32-bit PA-7100 LC processor. The third column shows an entry-level workstation running at 60 MHz, achieving a higher performance than the previous high-end machine running at 99 MHz. In fact, this entry-level workstation has only 1/8 the cache size of the previous high-end processor, and only about half the normal spec benchmark performance ratings for both integer and floating point performance. But surprisingly enough, it performs faster in MPEG video decompression than the otherwise faster machine, which did not have multimedia enhancements. The fourth column shows the same processor with multimedia enhancements running at 80 MHz and achieving 33.1 frames per second. Now this exceeds the real-time rate of 30 frames per second. These numbers show MPEG decoding running as fast as possible without being synchronized to the encoding rate. So although the video clip was encoded at 30 frames per second, the final column shows that the machine can decode at faster than 30 frames per second. To put this in context, processors without subword parallelism, whether PA-RISC or otherwise, would need to have much higher performance and much higher clock speeds to achieve the same performance as processors with subword parallelism. This is in fact true when we looked at experimental results reported for software MPEG decoding on other processors. In the next chart, we show MPEG video with MPEG audio decoding, also done in software, in the context of the entire MPEG video player product running in the mPower multimedia user interface. As you may know, MPEG audio is a complex audio decompression algorithm intended for high-fidelity CD quality music. Hence, the performance does drop a bit when MPEG audio decoding is also done in software, together with all the other layers of the software product. The chart shows three groups of columns representing the frame rates obtained from workstations using the same multimedia enhanced processor, the PA-7100LC, but at three different rates: 60 MHz, 80 MHz, and 100 MHz. The rightmost column in each group represents video only without audio. Now here, the video is synchronized to the encoded video rate, so that video decoding is not allowed to go any faster than 30 frames per second. The middle columns represent average grade audio. Here the audio is mono with half decimation, meaning that every other audio sample is used. The leftmost blue columns in each group represent the highest quality stereo 44.1 kHz 16-bit linear CD quality audio. While MPEG audio does degrade the performance of MPEG video decompression, it seems clear that video processing is still the key factor in overall performance. This is probably another reason why one tends to concentrate on the video performance requirements in any multimedia application involving video. This is the HP software MPEG player. It looks just like a VCR with a volume button, stop button, pause and resume button, and a play button. It also has a slider which allows you to move quickly to an approximate point in the video clip, and it also has fast-forward modes and reverse mode.
Think again. Hewlett-Packard.
Now the player also has the ability to allow you to resize the window without much noticeable degradation. This is the window at 1 1/4 size. And here's the window at 1 1/2 size. Here's the window at 1 3/4 size. Here's the window at twice the size. This video clip is being played from a CD-ROM and decompressed in real time.
If you think you have only two choices for business computer systems,
The MPEG player also has interesting functions like reverse mode, which is common for a VCR but really quite difficult for digital MPEG bit streams. Here we show how you can select reverse play. This is a feature of the MPEG player over and above what is defined by the MPEG 1 standard. With software video, getting another video stream running is as easy as just clicking on a button. Now notice that the frame rates have slowed down, but all three video streams are running in software. The following chart shows that these PA-RISC multimedia instructions are useful not only for MPEG decompression, but for other kinds of multimedia applications as well. This chart shows 4 applications run first without multimedia instructions on the left, and then with multimedia instructions on the right. The applications are color-coded. We can see that the same applications running with multimedia instructions are quite a bit faster than those running without. The speedup is anywhere from 1.9 to 2.7 times. Now you may ask, what is the use of being able to achieve frame rates like 67 frames per second for H.261 decoding when real-time needs are at most 30 frames per second for video or animation? Well, look at it another way. It means that there's more of the CPU left for doing other applications. This graph shows the percentage of the processor used when doing real-time H.261 video decompression in software. We can see that at a rate of 128 kilobits per second, less than 20% of an 80 megahertz CPU is used. Even at the very highest quality of 320 kilobits per second, only 26% of the processor is used. Hence, a large fraction of the CPU bandwidth is available for other computations. For example, in a video conferencing application, participants can share a map application while being able to see each other at the same time. Video conferencing with just talking heads is useful, but nowhere as useful as the ability to share other applications at the same time. Ultimately, as processors get faster, this will enable us to implement in software all the functionality of a true distributed meeting room, an application we had described at the beginning of this talk. In such an application, the computer could even give the illusion of a shared table, shared whiteboard, private versus public conversations, remote camera control, etc. All the functions one could perform if the virtual meeting room were a real one. What are some future directions for this work? In the first set of multimedia instructions that we introduced into the PA-RISC processor, we enhanced only the adder in the microprocessor. This allowed us to achieve significant speedup at very minor incremental cost to the chip. Yet there are still some other areas where we could get further improvement by using the same technique of subword parallelism on other functional units. For example, it's desirable to be able to rearrange the PEG subwords in the registers for further processing. Now, which operations are performance sensitive inner loop type operations will become clear as we optimize other large multimedia benchmark programs. Experience has taught us that it is much easier to add new instructions than it is to decommission old ones, even if they are seldom used. Hence, we prefer to add simple general-purpose functionality based on solid performance data from real programs, rather than introduce a large number of complex special-purpose instructions which may have limited use. Another area that would be interesting to look at would be real compiler support for these multimedia instructions. Currently, the compiler support is provided by means of macros in the C compiler. This enables the programmer to access the subword parallel instructions directly from a C program. However, imagine if the compiler could recognize such data parallelism in algorithms and be able to automatically compile loops using subword parallel instructions. Automatic compilation for data parallelism is a topic that is of interest to people working in many areas: high-performance parallel processors, multiprocessors, and in this case, Subword parallel microprocessors. We feel that exploiting data parallelism in compiling for Subword parallelism is probably easier than the other cases, since the degree of parallelism is low, in the range of about 2, 4, or 8 parallel subwords per instruction. And it is relatively easy to find linear speedup with this amount of parallelism, even for loops with only a few iterations. In fact, this may be the sweet spot for SIMD parallelism. One potential solution is to construct code schemas which define a style of programming of for loops using variables which are all defined as short integers. The compiler can recognize such a stylized loop as a potential candidate for compiling into Subword parallel instructions. The compiler basically executes these loop iterations in parallel using one parallel Subword track for each loop iteration. Another area that is very interesting for further exploration is the issue of architectural support to exploit hardware differences and hardware competitive advantages without losing software portability. Programming to the lowest common denominator is undesirable. How can we write programs that exploit different processor features, old and new, while still maintaining a single binary image? We have some ideas on this and encourage viewers to study this interesting and pragmatic problem. Now let's summarize what we have talked about. We have discussed the desirability of multimedia information processing on general-purpose processors to support various desirable communications applications. We talked about different approaches to multimedia support and why it's desirable to be able to support multimedia information processing in software. A software solution provides flexibility, low cost, and facilitates the pervasiveness of multimedia objects. We discussed multimedia benchmark characteristics and recognized that while there are many levels of multimedia programs, which should all eventually be considered, a fundamental level of multimedia processing deals with video and audio compression and decompression. We have shown an example of how real-time MPEG video decompression can be achieved with a high-level software program running on a general-purpose PA-RISC microprocessor in entry-level workstations. We described in detail the small set of multimedia instructions added to this PA-RISC processor. These multimedia instructions are generic single-cycle instructions that implement parallel operations on subwords within a word. We call this technique subword parallelism. The subword parallel arithmetic instructions have very low silicon and design complexity and no impact on system cost. They embed sophisticated computer organization techniques like SIMD parallelism in the RISC processor, with only minor changes to the processor. In a superscalar processor, they embed an even more sophisticated kind of SIMD-MIMD parallelism, since different operations can be executed in the same cycle. These subword parallel instructions can increase performance dramatically. They can effectively increase by 2, 4, or 8 times the computational power of current microprocessors with minimum changes. The beauty of these instructions is that they scale naturally with the processor, so that as processor performance increases, subword parallel performance will also increase. They allow high-end applications to perform well on low-cost desktops. Because they permit software solutions to hard problems, they facilitate pervasive access to multimedia information, since they minimize any need for add-in boards or special subsystems. Even when a processor gets fast enough to process real-time multimedia applications without subword parallelism, it is still a desirable feature. since it allows more efficient use of wide word-oriented data paths. This enables more of the CPU time to be used for processing other applications. The multimedia instructions described here are a subset of the multimedia instructions that will be a standard part of all 64-bit PA-RISC 2.0 processors, where increased data path widths and faster processors will result in a much higher multimedia processing capability, like MPEG 2 decompression rather than just MPEG 1 decompression. Some more multimedia instructions are also added for further performance gains. In conclusion, this minimalistic set of multimedia instructions enabled the world's first no-compromise MPEG player to be implemented with high-level software on a general-purpose microprocessor. Because of their general-purpose nature, these Subword parallel instructions can also be used to accelerate many different types of applications, multimedia or otherwise. Thank you.